The view from the edge of the exosphere, 480 kilometres above the surface of our planet, is awe-inspiring. 380 kilometres below lies the E layer, a 20-kilometre wide radio-reflective ionospheric layer between 100 and 120 kilometres above the surface of our planet. The ionisation of this layer is fascinating, as well as challenging for amateur radio operators around the world. This is the layer where ionised E-clouds live. E-clouds reflect VHF radio signals that would otherwise escape the Earth's atmosphere back to Earth. Our atmosphere has 5 layers. The lowest layer is the troposphere, which is where aircraft fly and where nearly all of our weather occurs. The stratosphere is next, with the mesosphere and the thermosphere above that. Sitting above all these layers is the exosphere, a place for spacecraft and satellites. Earth's atmosphere contains a series of regions that have a relatively large number of electrically charged atoms and molecules. As a group, these regions are collectively called the ionosphere. There are 3 main regions of the ionosphere: the D layer, around 75 kilometres up, the E layer, 110 kilometres up, and the F layer that starts at about 150 kilometres and extends upwards, sometimes as high as 500 kilometres. These regions do not have sharp boundaries, and the altitudes at which they occur vary during the course of the day and from season to season. Amateur radio operators take a keen interest in the tropospheric region of the atmosphere as well as the E layer, as these 2 regions can propagate VHF radio signals well beyond that of line of sight. The troposphere is the lowest part of our atmosphere, and what takes place within its boundaries largely determines our weather. Its upper boundary is the temperature inversion layer known as the tropopause, which lies between 8 kilometres and 16 kilometres high, depending on the latitude and prevailing conditions. The low level of ionisation is negligible as far as radio waves are concerned. However, small variations in the physical properties of the air give rise to variations in the refractive index, which results in several distinct tropospheric propagation modes. More about this in another video. The D region lies between 60 and 90 kilometres above the Earth's surface. It absorbs radio waves, particularly at HF, because the electrons are frequently colliding and dissipating the energy of the waves instead of propagating them. Although the D region is almost transparent at VHF and UHF, it does contribute to ionospheric forward scatter, especially when intense solar activity produces an excess of ultraviolet and high-energy X-rays, which can penetrate to this depth of the atmosphere. The E region is defined as that between 90 and 120 kilometres above the Earth's surface, and it can be regarded as the transition zone from the Earth's atmosphere into space. There are discontinuities in pressure, temperature, and chemical composition at this height. Above 90 kilometres, ions predominate over neutral atoms. Most of the shortwave ultraviolet rays and less energetic X-rays from the Sun are absorbed by ionising the E layer. Although the ionisation is normally insufficient to reflect VHF radio waves back to Earth, some thin and dense layers of ionisation occasionally occur, known as sporadic E. This is also the region where auroras and meteors produce ionisation capable of reflecting VHF and UHF signals. Above the E region lies the F region, which in daytime usually subdivides into two distinct layers, F1 and F2. The lower F1 layer plays little part in VHF propagation, except to contribute some refraction. If VHF radio waves are returned back towards the Earth, it's from the F2 layer heights. The F2 layer has an average effective height of between 300 and 350 kilometres, which can increase to between 450 and 480 kilometres. The layer varies between 100 and 200 kilometres deep. During the peak of solar activity, the F2 layer can provide worldwide contacts on the 6 metre band. However, the F2 layer does not reach the levels of ionisation required to return higher frequency VHF and UHF signals to the Earth, except in the special case of trans-equatorial propagation. Returning to the E layer, sporadic E is probably the most interesting and exciting form of signal enhancement for the amateur radio operator. Highly ionized patches, or clouds, occasionally form in the E region of the ionosphere. Known as sporadic E clouds, they're usually fairly small in size, but larger clouds or multiple clouds often form during substantial openings. As the name indicates, sporadic E is not easy to predict. After almost 80 years of study, the true cause of sporadic E is still unknown. There are many different theories as to how and why sporadic E clouds form. There seems to be no correlation between the ionization level or formation of sporadic E clouds and the 11-year sunspot cycle. But there is evidence to suggest that the primary cause of sporadic E cloud formation is wind shear, a purely weather-related phenomenon. Intense high-altitude winds travelling in opposite directions at different altitudes produce wind shear. It's believed that these wind shears, in the presence of the Earth's geomagnetic field, cause ions to be collected and compressed into thin, iron-rich layers, approximately 1 to 1.5 kilometres in thickness. The area of these patches can vary from a few metres to hundreds or even thousands of square kilometres. Along the same line is the theory that sporadic E clouds are formed in the vicinity of thunderstorms by the intense electrical activity associated with them. There is often, but not always, a correlation between thunderstorm activity and the formation of sporadic E clouds, enough to make the theory very feasible. However, strong thunderstorms often form along frontal boundaries, and intense wind shear is usually found along the same frontal boundaries that produce these thunderstorms. Likewise, strong sporadic E activity often appears when there is no apparent thunderstorm activity along or near the propagation path. Yet another emerging theory suggests that sporadic E clouds are formed by concentrations of meteor debris. Again, there seems to be a strong correlation between meteor shower activity and the number and intensity of sporadic E clouds. It's all speculation though, as nobody has presented a definitive explanation for how and why sporadic E clouds form. The amount by which the path of a radio signal is refracted by sporadic E clouds depends on the intensity of ionization and the frequency of the signal. For a given level of ionization, the signal refraction angle will decrease as the frequency is increased. Above a certain critical frequency, refraction of the signal will be insufficient to return it to the surface of the Earth. This critical frequency is known as the maximum usable frequency, or MUF. Sporadic E is very common on the low VHF frequencies during the summer months. It's not uncommon for the MUF to rise up to and stop at a particular frequency within the FM broadcast band. Distant signals will be heard below the MUF, while only local or tropospherically enhanced signals will be heard above the MUF. Over the years, it's been observed that the signal strength of the received sporadic E signals will be greatest just below the maximum usable frequency. Since the bending angle, or angle of refraction, decreases as the signal frequency is increased for a given ionisation level, we can surmise that the most distant receptions will occur as we approach the maximum usable frequency. In other words, an E-cloud will support longer signal paths at 100 MHz than it will at 50 MHz. In this example, E-cloud 1 is more intensely ionised and thus capable of refracting signals at a sharper angle, producing a shorter skip distance for a given frequency. Signals being refracted by E-cloud number 2 are returned to Earth at a lesser angle, thus producing longer skip distances. With clouds 2 and 3 in alignment along a signal path, double hop skip can occur. With this cloud alignment, signals from both the transmitter and the signal hop zone would be heard at the receiving station. The maximum distance for a single hop sporadic E propagated signal is about 2,500 kilometres. However, if multiple sufficiently ionised patches exist in a line along a particular signal path, this can extend the range of E-layer propagation signals out to around 5,000 kilometres and beyond. If the midpoint of a double hop happens to be on the water, such as the ocean, the signals will be stronger and there's less likely to be interference from midpoint stations. Sometimes we hear sporadic E stations that don't seem to fit the normal model in terms of path distance. It's not uncommon to receive signals beyond the range of what would be considered normal for a single hop, but less than the range expected for a normal double hop. There have been many theories to try and explain this phenomenon, including paths along multiple sporadic E clouds. In this example, neither E cloud is sufficiently ionised to return a single hop to Earth. With two weak clouds working together, the refraction angles of both ES clouds are essentially added. This would have the effect of raising the apparent maximum usable frequency and ultimately returning the signal to Earth at a greater than normal E distance. This would account for the variable path distances which fall between that of single and double hop sporadic E path distances. Although sporadic E may appear to give an improvement in some HF communications, it can also have the effect of degrading some HF signals. However, the intermittent nature of the sporadic E clouds and the fact that the clouds are very mobile means that any effects are likely to be relatively short-lived.